Hello everyone, welcome to lecture 17. In this lecture we will continue the discussion on the application of remote sensing for floods. So in the previous lecture I started discussing about the application of remote sensing in precipitation estimation, right. So in this lecture we will continue that and we will see more detail about how we can identify or how we can estimate the precipitation. So, satellite remote sensing techniques to estimate precipitations are infrared remote sensing techniques and microwave remote sensing techniques. So, we are using both infrared and microwave. When we talk about the infrared, here we study the relationship between the cloud's temperature, cloud top thickness and the precipitation. And then we try to come up with a model which can provide us the information about the precipitation probability of a particular cloud. Colder cloud top temperature indicate higher and thicker clouds which supports heavier precipitation. Now here you can see, based on the observation we have come up with this particular statement that colder cloud top temperature indicates higher and thicker clouds, and if we have higher and thicker clouds which will support the heavier precipitation. Now the next is relationship between changes in cloud top surface and precipitation that will help us to indicate that vertically growing clouds are associated with precipitation, right. Rainfall at the surface is related to cloud top properties observed from satellites. So, we will see how these remote sensing data sets are an indicator of precipitation. When we talk about the visible reflectivity, if we use this data, brighter or thicker cloud, that will lead to heavier precipitation. Dark means no rain, right. When we use IR brightness temperature, again we are talking about the infrared remote sensing images. So here if it is colder, that means heavier rainfall, and warm means no rain. So you need to see the relationship between the temperature, which wavelength you are talking about, and then how it is related to the precipitation. When we use NIR brightness temperature, here we use this relationship, and if it is equal to 0, that means rain is more likely to occur, right. And here the large drops or ice will be found, right. When we have this greater than 0, then small water drops will be found and no rain is expected. In this particular spectra, you can see different types of snow grain radius are plotted. So, here if it is 0.005, this color is indicating, right. Blue is 0.5 mm. So, here you can see this is 0.5, 1 mm, that is here in the yellow color, and green is 0.2. And here this is optically thick clouds. So, you can see how these absorption features are coming in different grain sizes. So, here one thing you can easily observe, that if we are having change in the grain size, right. So, this intensity is increasing, right, but the pattern remains same. And when we are talking about the optically thick clouds, it is different from these, right. So, this is how we can identify or separate these clouds from the snow in the high altitude areas, right. So, it is very easy when we are having the high spectral resolution data, and referring to the band ratio concept, and based on that we have several indices, and similarly we also have some indices for the water, right. So, now if you refer to this microwave remote sensing, the direct relationship between ice in cold clouds and precipitation, that says ice scattered terrestrial radiation back to the surface and appears cold in images. So, cold means the temperature will be low. The direct relationship between water content in cloud and precipitation using microwave remote sensing. So, here it says water in clouds emit microwave radiation, and we are referring to this passive microwave, and appears warmer in the image if high water content clouds are present. So, this is how we correlate and we try to estimate the precipitation using the microwave data set. The passive microwave data from a polar orbiting satellite, these are very popular in precipitation estimation. Rainfall at the surface is related to microwave emission from raindrops. Low frequency channels are used, and microwave scatters from ice, that is high frequency channels, right. These concepts are utilized and then the meteorological parameters are estimated. Low frequency channels, here you can see the warm, many raindrops and heavy rains are expected. Cold, that means no rain. High frequency scattering channels, that means the cold scattering from large ice particle and heavy rain is expected. If it is warm, then no rain is expected. So, this is how we utilize microwave remote sensing. Now, we will be referring to the microwave utility in flood studies. So, before that we have to understand the basics of microwave, though I have covered in the microwave lectures, but again I will be referring back to them, and then we will try to understand which and how microwave remote sensings are used in flood studies. So, starting with the very basic, SAR data sets are crucial for flood monitoring due to their ability to operate through clouds, because we are talking about the natural disaster flood, right. And whenever we have flood, it is expected that we are having the high rainfall in that particular area. If that area is having high rainfall, that means cloud cover will be there. If the cloud covers are there, optical remote sensing will be not of that much of use, right. So, in such situation, microwave remote sensing will become the important source of information, because without visiting the area, we will be able to identify the changes and the inundated areas, right. Optical sensors are often ineffective during floods because of persistent cloud cover. As I said, SAR uses microwave with longer wavelengths, right. Remember, we are talking about the longer wavelength and we are measuring the backscattered energy, which can penetrate clouds and collect surface data. Wavelengths are long, so it is expected that clouds will not have any interference in our data acquisition. Its active nature make it reliable for time sensitive flood mapping regardless of weather or light condition. So, even in the night time we can have this measurement when we are talking about the active microwave sensors, right. So, here you can see the optical remote sensing and SAR images. So, this particular river, how they appear, right. So, when we talk about the optical remote sensing data, here we have the option to visualize this particular river in true color composite or false color composite. But when we talk about the SAR data, here the backscattering energies are measured, right. So, these energies are measured and then we will be able to identify the features on the ground, right. So, modern use of SAR for flood detection. Accurate flood mapping is crucial for assessing damage and planning relief efforts, because sometimes if the area is inaccessible, if we are not able to travel that particular area or visit that particular area to estimate the damages or to provide the mitigation measure, then we will have this microwave remote sensing to accurately identify the flood inundated areas. Today's SAR system offer higher resolution and frequent acquisition, because temporal resolution is also important here, and the temporal resolution of current microwave data sets are very high. So, for example, Sentinel-1 is having the data acquisition at every 12 days, right. So, that is the revisit period for Sentinel-1. Flood detection via SAR often relies on thresholding backscattering levels. So, what happens? If you remember in the classification, I said if you have the DN values ranging from 0 to 255, you can go for the density slicing, right. So, here we will be using the thresholding, which can segregate the water from the non-water areas. Integration with some other sensor enhances flood detection accuracy. You can also utilize some other microwave data sets which are measuring in the different wavelength region, or you can also utilize the optical remote sensing data set here, that will enhance or increase the accuracy of your estimation. Challenges include terrain type and surface condition, which can affect backscattering interpretation, right. Here to explain the different viewing geometry of the microwave sensor, I am using the same slides. So, hope you will be able to understand easily. So, here this is the aeroplane I am referring to, and here we have a sensor, right, and this is the nadir, right, which is perpendicular on the ground, right, and this is the beam which is illuminating this particular area. So, this is the horizontal plane, right. So, flight is moving on this. So, here the center line of this viewing angle, that will be your slant range, and this will become the image center, right. So, here we refer to flight direction A and nadir B, right. So, this is perpendicular on this ground, right. So, the microwave beam is transmitted obliquely at right angle to the direction of flight illuminating a swath C, which is offset from nadir. So, you can see this is offset from nadir, it is illuminating this particular area, and the range D, which is referred to across track dimension perpendicular to the flight direction. So, this is D, and the azimuth E refers to the along track dimension parallel to the flight direction. So, this is the flight direction. So, nomenclature, I hope you will remember it. So, this is what we have, the incident angle, right, and with the nadir it is making the look angle. So, this is the beam which is falling on this particular surface, right, and with the flight direction it will make the depression angle. So, here one by one we will see. So, this is your, you see the animation, it will be very clear. So, the depression angle, then we have look angle, then you have incident angle, then you have near range, right. This is the far range, this is the slant range, this is the beam width which is illuminating in both sides, right. So, here this is another representation of viewing geometry of microwave remote sensing sensor, how it generates the data using this particular configuration, right. Now, we will try to understand the different scattering mechanism. So, let us talk about the surface or diffused scattering. Keep looking at this particular animation. Diffuse scattering occurs when a microwave signal hits a rough heterogeneous surface. Roughness of the surface is determined by the wavelength of the microwave signal, right. For example, bare ground. Here I am taking the example of bare ground. Then comes the specular reflection. So, again keep watching this. Specular reflection occurs when the radar pulse hit a smooth or flat surface relative to its wavelength, right. These pixels appear in a dark tone low backscattered value will be measured. So, for example, calm water body, roads, airport runway, those will be very calm and these values will be dark tone, right. Then we have double bounce or dihedral scattering. This scattering occurs when the radar pulse hits two perpendicular relatively smooth surfaces, right. These pixel appears in a very bright tone and we will measure the high backscattering value. For example, building, tall trees, those are the examples of this dihedral scattering. Now we have volume scattering. Volume scattering occurs when the radar penetrates a 3D body and interacts with particles sensitive to the wavelength. So, here you can see the rough surface, right, the natural body. So, here you can see the multiple scattering is happening at the same time and only a part of it is returning to the sensor, right. For example, tree canopies, dry snow, vegetated fields, these are the examples of volume scattering. Now, we have learned all the different scattering mechanism. Now, we will see how these backscattering values or backscattering mechanisms are used in flood studies. So, backscatter is the amount of radiation received from a particular illuminated target. It varies significantly between different land cover and land uses. We have learned that different scattering mechanism will have different values, right. The darker tone, it appears due to specular reflection of the water body. Now, it is only related to flood studies, right. So, this darker tone will be related to water bodies and here the brighter tone, it will be due to dihedral scattering of urban structure. Now, here you can see all these are water bodies, right. So, here the value you can see this will be low, right. So, when we talk about the flooded area, smooth water surface reflects radar waves away, making flooded areas appear dark, that we have learned in the previous slides also. Land areas scatter waves back to the radar, creating contrast for flood mapping. So, one object is very dark, one is very bright, then clearly you will be able to mark the presence of water. That is the first and foremost thing we do in the flood studies. So, this way behavior is altered due to wind and urban and vegetated areas, because that will be the problem. So, roughens the water surface because of the wind, hence increasing backscatter and making it harder to distinguish from land. Because of the wind, you will have different backscattered value for the water and then it will be camouflaged with the building or any other structure. Urban and vegetated areas, double bounce effects from building or flooded vegetation and volume scattering can elevate backscattered, confusing water classification. So, these two are the major problem when we use the microwave data in flood studies. Age effects and misclassification. Extended vegetation at flood boundaries hinder accurate flood age detection. So, what happens if this is the boundary of the flood water and here you have the very dense vegetation, right. So, what will happen, the boundary you will be confused whether it is like this or like this, right. Water like surfaces like road, roofs, due to the similar scattering mechanism, this flood water can be over predicted. So, the area estimation will not be sometimes very accurate. Layover and radar shadow, that is another problem. In cities, layover hides flooded streets under prediction of floods. Radar shadow behind building or slopes can mimic flood zone. Over prediction can happen at this particular moment, right? Because if you see, this is the building and your sensor is here, it is looking at this particular area. So, this side will be the shadow zone, right? So, here you will be estimating it, but this estimation can lead to the overestimation of the area, right. So, the parameter which are affecting the backscattering value when we are talk about the flood studies, flooded areas cause specular reflection leading to low radar backscatter. This creates a high contrast between flooded and non-flooded terrain, right. However, this radar backscatter behavior is influenced by system parameter and the ground parameter. So, what are the things we have in the system parameter? They are wavelength and frequency, then we have polarization, then we have incident angle. When we talk about the ground parameter, wind induced surface roughness, we have seen that because of the wind, we will have the over prediction or under prediction of the water, right. Then next is the soil moisture, topography, vegetation and urban signature, which can camouflage the actual flooded region. So, these two parameters influence greatly the study of flood in using microwave data sets. The system parameter, the wavelength. So, the penetration through the canopy increases with wavelength. So, as we are moving towards the longer wavelength within the microwave domain, we will have better canopy penetration, right. So, here you can see this is X band, this is C band, right, and here you have L band. So, how microwave energies are interacting with the canopy or the vegetation in this particular condition. Common operational range of spaceborne microwave imaging. So, here you have X band, C band, S band, L band, P band, right. Here the frequencies are given and the satellites which are available nowadays, it is mentioned here. Even some of the upcoming missions are also mentioned here, right. Signal penetration into inundated vegetation for varying wavelength. So, this Manu National Park, Peru. So, here you can see the C band, L band and P band are used. So, here the same area has been represented. So, this is the same river channel, right. Now, you see the difference. Yourself can identify which particular band is better in estimating the flood prone areas. Flooding under vegetation is undetectable using C band SAR, right. This is C band. While L band can identify inundated under moderate vegetation cover, right, which is this one, and the P band effectively detects flood water beneath dense vegetation canopy. So, if you are talking about the flood studies in the high vegetated areas, then preferably we will be using the P band data set. If it is not available, we will go with the next choice, which is L band, but in C band these inundated areas are not visible clearly. Here you can see the land surface appears smooth to a long wavelength radar, right. Little radiation is backscattered from the surface. The same land surface appears rough to short wavelength radar. The surface seems bright in the radar image due to the increased backscattering from the surface. This is the condition, right. So, a surface is considered rough if this satisfies this particular condition, where we are using the height of surface irregularities, SAR wavelength and the incidence angle. So, this will be able to help you which particular wavelength is better for your study. Then comes the polarization. I hope you remember these basics I have covered in the microwave remote sensing. Now I am referring those concepts again here to understand the application or application potential of microwave remote sensing in flood studies. So, the polarization indicates the direction of travel of an electromagnetic wave. Linearly oriented features like building tend to reflect and maintain the coherence of the polarimetric signal, hence more effectively detected in copolarized channels, right. Randomly oriented elements such as tree, leaves cause multiple scattering leading to signal depolarization, therefore detected in cross polarized channel. Cross polarized, if you remember VH, HV, these are cross polarized. Then like polarized HH, VV, right. So, here these two are like polarization and these two are cross polarization. So, cross polarization will be able to help you in flood studies. HH polarization is more effective than VV or cross polarized mode for detecting water, right. Beside, HH polarization performs better in windy condition. VV is more sensitive to wind induced waves. Combining multiple polarization, for example HH and VV, can improve flood mapping accuracy. So, here earlier in the previous slide I told you that cross polarization is better, right. Now, here depending upon the situation I am saying that different polarization is more useful, right. So, it is not a thumb rule to use cross polarization or like polarization. Depending upon your condition or the condition of the study area, you use the different polarization data sets, right. Combining different radar bands is also helpful. Polarization enhances land water discrimination, which is especially useful for vegetated and urban areas. So, not only C band or L band or P band, you can also refer to different microwave data sets which are available from different sensor, and if fortunately those are available for your study area measured at the same time, then you combine them and together it will be more useful, right. Now comes the incident angle. So, here you can see the contrast is generally higher at larger radar incidence angle due to a shaper decline in water surface reflectivity. So, here you can see this is no flood and this is flood. Terrain tends to remain relatively bright due to broader scattering irrespective of the value of theta, right, that is incident angle. At lower angle, water appears bright, reducing the contrast. Intermediate angle used in satellite hardly show this behavior clearly, because we are talking about the space measurement. So, it will be very hard. Now comes the surface roughness. So, strong wind roughens the water surface, because of the ripples it will appear rough, right, and the same time we are having the microwave measurement. So, it increases radar backscatter and reducing contrast with terrain, because earlier when it is calm, then what will happen, we will get less value for the water, the darker pixel will represent the water. But because of this wind, what is happening, the roughness is increasing and the backscattering value will be more. So, it will be very difficult to segregate this information with the topography or the other features like urban areas. This makes flooded area appear less dark and sometimes indistinguishable from land. Hence, accurate wind data acquired during the flood event is very important. Factors like water depth, obstacles and terrain add to modeling complexity, right. With this, I will end the part 1 of this lecture. We will continue this lecture and we will continue discussing about the limitations of the microwave remote sensing in flood studies, and then what parameters we should choose carefully to utilize this information in flood studies. Thank you very much.